Thanks, everyone. My name is Justin. I work at Microsoft on PyTorch exporters and ONNX tools, etc. And this will be an update for the Convertors SIG, which is led by Kevin from NVIDIA, as well as Xavier from Microsoft. I don't think Kevin's here, so I'll be doing the presentation. With the past year, we've made a lot of, so we start with the Torch exporter. That has been the most active converter for ONNX. And with the last year, we've made a lot of progress in terms of the converter in PyTorch itself. The converter that we're building, and you may remember that we've been using Torch script for capturing the model, and we built a converter based on Torch script for ONNX. The converter that we've been building for the last year and longer has been this dynamo equals to true option. It has been added from Torch 2.5 with additional options like report and verify for users to understand the export process and understand any errors that may happen. So the API looks like this, and this is kind of only thing that is new is the dynamo equals to true option right there. And the kind of how you would use it is very familiar, should feel very familiar than how you would use it before. Last year, it has been this dynamo export API that we released as an experimental API using the dynamo technology in PyTorch for capturing the graph. And this particular API has been deprecated and has been merged into the dynamo equals to true option. So for the Torch script-based exporter, the plan is to deprecate it. It has been very popular and widely used. So deprecation doesn't necessarily mean the removal of the option if Torch script isn't going anywhere. So we expect that it is going to follow how PyTorch core is handling Torch script. So when it comes time to deprecate Torch script itself, that's probably time when dynamo equals to false option is going to go away. But then the plan is to make dynamo equals to true to default in a few releases when it stabilizes and we bridge the remaining gaps. And it's now tracked by a GitHub issue that you can look at. Now, the new ONNX export flow looks like this. First, we leverage this new Torch export API that captures an exported program to describe the model behavior. We run decomposition with an ONNX decomp table, which essentially transforms the exported program into something that we have implementation with ONNX ops. We then translate to ONNX using the new ONNX script implemented Torch lib library, which is a new implementation that maps A10 operators or PyTorch operators into ONNX operators. And we build a graph using ONNX IR, which is this thing that I'm going to give a presentation next. After that, we obtain an ONNX model. And unlike previously when we used Torch script, we do a lot of graph-to-graph transformations with the PyTorch API. We now have the means to do those transformations with ONNX IR and run different optimizations and passes directly on the ONNX model. And with that, we get the final ONNX model that users can serialize to disk. The first nice thing with the new API is that the return object is going to be an ONNX program. It is essentially a wrapper around two things. One is the exported program that Torch export produces. And the second thing is the ONNX IR model. You can get the ONNX IR model with ONNX program.model. And you can get the familiar ONNX model proto with program.model proto. and there is a simple kind of save API for you to save it to disk. What's nice about it is that it is now a callable that can accept torch tensors. So it makes it really easy for you to kind of run the program and verify and ensure that the program is behaving the same as your NM module in PyTorch. Next, we have dynamic shape support. With the adoption of torch export, what becomes needed is a new way to represent dynamic shapes because how the internals of torch export is expecting this information. Now the dynamic shapes is a new parameter on torch ONNX export that's slightly different from the dynamic axes option that we used to have. And you need to provide that following the input data structure. Essentially, if you have a list as input example tensors, then you would provide the dynamic shapes in a list as well, just to follow whatever that you input. And you can see in this example, the list input is exactly a Python list, and that's how you provide the dynamic shapes. With the O exporter, how typically we support control flows, the if statements and while loops, is that we use torch JIT script to kind of parse the Python code and kind of emit a torch script corresponding graph in torch script so that we can capture control flows. With PyTorch 2.0 and a new export, you would need a torch.conn expression for capturing the control flows. How you would use it is by calling torch.conn, provide the conditional and 2 branches. PyTorch is able to leverage Torch Dynamo to capture the 2 branches so that it's complete in the graph. So that's how you would do it with torch.conn for control flows. That does mean a little bit of model rewrite. So we're exploring with the export team over at Meta as well to see how we can bridge this and make it easier for users. Some of the ideas has been, for example, using Torch JIT script to capture some of the control flows, but then make it compatible so that the Torch Export API is able to capture those graphs. With the introduction of new ONNX offsets, we also added support for the new operators in export. Examples include group normalization, JILU, and more importantly, the attention operator that was just added. To use it, you would simply set offset version equals 23 and use the scale.product attention operator inside PyTorch, which gets translated directly into the attention operator so that you can save a bunch of work trying to fuse those nodes. There's also the introduction of rotary embedding, and I will show in next slides how you can use it as a native operator, because that's something that doesn't exist in PyTorch, and we now have a nice way for use ONNX operators natively as PyTorch operators in your NM module. But before that, there's also metadata included now. That is some rich metadata that we infuse into the ONNX models, and we didn't have this before. So you can see a few examples right here. We have the namespace for you to understand where an operator belongs in terms of NM module hierarchy. We have the class hierarchy and FX node so that you can directly correspond your ONNX operators to, for example, your exported program or even the source of your NM modules. So that makes debugging very easy because you know exactly what is emitting those nodes. You can even have that stack trace so that you can just click into it and find a line that is emitting the node. So that's a bunch of things you can use for either debugging or even downstream analysis and optimization by directly leveraging the knowledge of the NM modules. Now, this is the exciting bit. We have the symbolic and native ops supports in 2.8. That's what I was alluding to with the rotary embedding operator. With Torch ONNX ops symbolic, you can embed any ONNX operator as a symbolic operator inside your FX graph. And if you're not familiar with FX and export program, FX is the PyTorch IR that is used inside an exported program to describe the PyTorch model. So you would just use either a native ONNX operator or a custom domain, any custom domain operator. Given the input and attributes, you need to specify the data type and shape because we don't have any information of those operators. But then given these simple information, it's going to now appear as a symbolic operator in the FX graph. Now, granted, you cannot run the operator as kind of native PyTorch operator, but it is going to show up in your ONNX graph. So that makes it very easy if you want to, for example, replace a block of code with your custom operator. Previously, you need to register and make the exporter understand it. Now the exporter natively understands what you're trying to do and is going to emit that operator for you. What is now even better is that we have implemented some operators as native PyTorch operators. And the first example is this rotary embedding. With Torch ONNX Ops rotary embedding, what is possible now is you can just use it directly in your NM module and run it natively as whatever PyTorch program that you have. It's compatible with the Torch export logic. It's also compatible with the run decomposition API. So even though it shows up as a ONNX domain operator inside your ONNX graph, you can call run decomposition, and it's going to now emit a bunch of A10 operators for you. So that is kind of natively compatible with all the PyTorch ecosystem. But when you export the ONNX graph, you're able to get a rotary embedding operator directly without having to go through a different, without having to jump through different hoops. Next, we have improved the verification tools that we provide in the Torch ONNX module. We now have this single API that is verify ONNX program. What it does is it takes the ONNX program that you provide or that you obtain from ONNX export, which contains the exported program from PyTorch and the ONNX model in the form of ONNX IR. Because we thoughtfully name the values inside the ONNX graph to be, to correspond to the actual nodes inside the exported program, we have a means to verify all the intermediate values that is produced by the ONNX model, so that it makes it very easy to spot any discrepancies during the conversion and pinpoint exactly what is going wrong. It could be that some implementation of the conversion logic is incorrect, or it could just be that whatever backend or specific environment that runs the model produce kind of numerical precision errors, and you'll be able to observe those as well. With the Model Explorer and this Model Explorer ONNX plugin, we're able to visualize that result as well. So you can see all the green nodes are where we find the discrepancy to be very small or zero. And the orange and red node just means that the discrepancy is happening, and that makes it very easy for you to kind of dig in and understand what's going on there. And finally, we have this conversion report that is enabled with the report equals to true option. this essentially gives you a markdown report of the whole export process. If any error happens, it will give you the error message and the full stack. It will also print the exported program and the generated ONNX model for you to examine so that you can, all the intermediate information is available to you. And if you want to report that to the developers or to us and say, okay, you are doing this thing wrong or we found a bug, that is an easy means for you to do that. Now, some future work for the Torch exporter. We want better control flow support, which is what I previously mentioned. Maybe understanding Torch JIT scripted functions would be beneficial. We want to also support potentially the different quantization methods and quantization frameworks that's popular in the PyTorch ecosystem. Right now, quantization is not very well supported in the new export path. So what you would typically do is you may want to kind of manually replace some quantized module with something that the exporter understands and do some post-processing so that it becomes the form of QDQ representation, if you wish. We're also looking at flex attention support, and that's being looked at by the GenAI working group so that whatever flex attention operator that the user is creating can be translated into the ONNX graph as well. And finally, some other converter updates that includes TensorFlow, on the list, TensorFlow, scikit-learn, and XGBoost. They respectively have a new version that's released and some support for latest or newer offset versions. They're relatively kind of stable right now, and not much development has gone into supporting these converters. But if you find one of those converters is useful to you, we welcome your contribution to these converters. Now, I think Xavier has also added a few slides on some of the additional future thoughts for converters. I'm not going to read them right here, but it will be distributed as material. And if you have questions or comments for any of these, we're happy to hear them. All right. So please join us on the Slack channel, on the ONNX Converters Slack channels to have more discussion. For the PyTorch converter, we also have we also actively monitor the PyTorch issues, so you can tag us with the ONNX tag. And please subscribe to the mailing list for more updates. And that's everything. Thank you.